Hello, in this video we are going to solve the following problem for you, Mathematical Olympiad, number theory, Diophantine equations. Determine all prime numbers p and q such that 20 times p cubed minus q cubed equals to 1. Pause the video at this point and give it a try. If you find the problem hard, on the next slide I will provide you with a hint. If you don't want to see the hint, please pause the video now. Hint number 1. Use Fermat's little theorem for some appropriately chosen module. This theorem states that if capital A is an integer and capital P is a prime such that the GCD of A and P equals to 1, then a to the p minus 1 is congruent to 1 module p. On the next slide, I will provide you with another hint so that you see which module is suitable to work with here. If you don't want to see that, please pause the video at this point. Hint number 2, choose 7 as the appropriate module in Fermat's little theorem. On the next slide, I will show you the final answer to the problem. If you do the problem correctly, you will see that there is only one pair of solution to the problem. P equals to 7 and Q equals to 19. Okay, so now let us solve the problem. So as I have provided you the hint, it is good to go to to module 7. So if from here I can conclude that 2p cubed minus q cubed is congruent to 1 module 7. But we also know that 20 is congruent to minus 1 in module 7 because 20 minus 1 is 21 and 21 is divisible by 7. So this means that another name for 20 when it comes to module 7 is just simply minus 1. So this becomes minus p cubed minus q cubed is congruent to 1 module 7. And for simplicity, if you don't mind, let me multiply both sides by minus 1. Then I will get p cubed plus q cubed is congruent to minus 1 module 7. Okay? But now let us use as I gave you the hint, use the Fermat's little theorem, so which tells you that if A is an integer and P is a prime, so that GCD, the greatest common divisor between A and P, is equal to 1, then you can conclude that A to power P minus 1 is congruent to 1 module the prime number P. Okay? So this is the content of Fermat's little theorem. Okay, and I have given you the hint that use P to be 7 here. So what I can write, I can replace A with this little p and replace capital P here with 7. So I want to give the role of A to P, this P that I am looking for, and I know it's a prime number. Okay, and I want to replace this capital P as the module with 7. So then what happens? If GCD, this is crucial, if GCD of A, which in this case is my P, and capital P, in this case 7, is 1, then I can conclude that A, which is little p, to power capital P minus 1, which in this case is 6, will be congruent to 1 module 7. Yes? So remember that in Fermat's little theorem, we don't demand that A be prime. But it doesn't hurt if it is also prime because it works for integers, including prime numbers. So this is what I have. Then what does it mean? If I move 1 to the other side, it means p to the 6 minus 1 is congruent to 0 module 7. But what does it mean? It means 7 divides p to the power of 6 minus 1 But then you can immediately see that I can factorize this using the conjugate rule. So it becomes p cubed minus 1 multiplied by p cubed plus 1. Okay? But we also have a theorem that if I have a prime number which divides the product of two numbers, a and b, we can conclude that p divides a, or, this means or, p divides b. In other words, if the product of two integers is divisible by a prime, then at least one of them should be divisible by that prime. So here I have a product of two integers, which is divisible by 7. And I know that p is a prime number, supposed to be a prime number, so this coefficient is not 0. So this means that either this one is divisible by 7 or that one is divisible by 7. So it means that 7 divides p cubed plus 1 or 7 divides p cubed minus 1. But if I want to translate it in the language of congruency, this means that either p cubed is congruent with minus 1 module 7, or p cubed is congruent to 1 module 7. So this means that what happens to p cubed plus q cubed, that is important. So I can do the same analysis for q, because you see that here I chose p to be a prime number, which is which has GCD 1 with respect to 7. If that is the case, that GCD of q and 7 is also 1, I can conclude the same thing for q cubed. So this means q cubed, when it comes to module 7, is either minus 1 or 1. So what happens for the sum? If both of them are congruent to minus 1, when I add them up, it will be congruent to minus 2. If both of them are congruent to 1, when I add them up, it becomes 2. But if one of them is minus 1, the other one is 1, when I add them up, it becomes 0. So this means that if p is a prime number, this is true, and this is true if this is true. Similarly, if this is true, I can conclude analogous statements for q cubed. But in that case, I hope that I could convince you that the options that we have for p cubed plus q cubed is either 0 if one of them is minus 1, the other one 1, or 2 if both of them are 1, or minus 2 if both of them are minus 1. But this does not fit with this assumption, because if you gave me this, I could grant this, but minus 1 is not congruent to any one of these numbers in module 7. So this means that if I assume this and I assume this happening simultaneously, I have a contradiction, because this one and that one cannot simultaneously work out. So what does it mean? It means that either this one should not be correct or that one should not be correct. So this means that, for example, so it means that either GCD of P and 7 is not equal to 1, or GCD of Q and 7 is not equal to 1. Or both, of course, because when we say both, when we say or in mathematics, that is an inclusive or. So it considered both cases simultaneously as well. But on the other hand, because p is a prime number, if I ask you what can you say about GCD of p and 7 in general, you know that should be a number that divides 7 and divides p. So this means that this number is either 1 or 7. If it is 1, I am in trouble. It doesn't work. So this means the only option that I have is that this is a 7. Okay? So if that is 7, then what can I conclude here? It means 7 should divide p. But p itself is supposed to be a prime number which is divisible by 7. It is only 7. So p becomes 7. Okay? So this condition that this one is not equal to 1 if p is a prime automatically means that p is 7. And by the way, is this acceptable or not? I don't know. I have to go back and put it in my equation to see that if I can find q. So if p is 7, I put it there, so it becomes 20 times 7 to power 3 minus q to power 3 is equal to 1. And then q to the power of 3 becomes 20 times 7 to power 3 minus 1. And then if you calculate this, I use my calculator, so I calculate this one, take the third root, and it becomes 19. And fortunately, 19 is acceptable because q is supposed to be a prime number, and we know that 19 is a prime number. So this means that one possible solution is p7 and q equals to 19. But the other scenario might be this is going to happen. But this will not give rise to any acceptable solution, because when you say GCD of a prime number q and 7 is not equal to 1, exactly as I explained here, you can conclude that because q is a prime number, q has to be 7. But if I replace q with 7 in the original equation, so 20 p cubed minus 7 to power 3 equals to 1, and if you solve for p, this becomes 1 plus 7 to power 3 divided by 20, and then you can immediately realize that this is not working, because this becomes 344 divided by 20, which is not even an integer. So there is no solution coming from it. So this analysis guarantees that there is only one pair of solutions. P has to be the prime number 7 and Q has to be the prime number 19. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.